For today's quiz, we're looking at a very large thrust bearing, and a thrust bearing allows one horizontal plane to essentially be frictionless with another horizontal plane. Now, bearings are not absolutely frictionless, but they reduce it tremendously. What I've done is I've taken this apart, and you can see the race here where the balls for the ball bearing would rest. I put 18 of them around in a circle here. That's the maximum that I could get on. And these are 1/2 inch ball bearings. And I'll just put that back on. And from there, you can get this to rotate. Our question for today, and it's not just a quiz. We're going to make this into a long term and show you how to do these. But our quiz today simply asks, if I wanted to have these rotate and I took one bearing out at a time, so we decrease from 18 down to the lowest number, how would that influence the amount of time that it would rotate if I gave it a good spin? Here's what your quiz looks like now. I'll hold that up. As always, mark your answer as completely as possible and list your level of confidence. All right, typical student responses for the quiz would be that a lot of students will say, well, I've seen bearings before. You need the full set of those spheres in there for it to function properly. So many would say you need all of them. Others might say, well, each one of those maybe adds a little bit of friction. So maybe if you decrease them, they would spin more freely and for a longer period of time. Those are the typical answers we'll get from our students. Instead of just providing a typical explanation, we're going to use this as a long term. And what are long terms? Long terms are anything where you find it interesting and you'd like to know the answer. So in this case, I had these races laying around. I put a few ball bearings there and I just started playing with it. I'm interested in this. Anyone who likes mechanical devices usually likes bearings. First thing that I did when I was putting more or less of these spheres on, I took one away and I noticed right away it spun much more freely. And I could see that because when I put these in, it barely fits on there. And these do not want to spin. So my claim right away would be that as I take these ball bearings away, they are going to end up spinning more freely. So that's what I'm going to make a claim about. And claims are just a way to give you direction. I now am going to take these off and I'm systematically going to investigate this. I better figure out a way to time it because I could either do rotations or I could do time. I think doing time would be much easier. So I'm going to set up my cameras and get it ready. And then what I'll do is I'll take each run, I'll take a bearing away and I'll record my data. When we were off camera, I ended up making a table here. And I thought, I'm going to need to collect data. And I don't exactly know what I'm doing, but you just got to get started. So my plan is, I'll just kind of give it a rotation. I'll use this phone. I have a stopwatch function on here that I'll use. And then I'll just record the data. Now, one of the things I recognized right away is when I have more spheres, it definitely ends up having more drag. So I know that my smallest number of bearings that I could have on there, or balls that I could have in there, is 3, because you need 3 points to make a plane. And I can already tell it is going to end up going for a longer time with 3 as opposed to 18. In fact, the 18, it's really hard to even get any value on it all. And because I don't exactly know how I'm going to do this, I'm going to start with what I think is going to be an easier time to measure, 3. So I'm going to take and get rid of these. Now, that's the essence of a long term. No one knows exactly what you're going to do, including you, but you just get started. You're going to make revisions. You're going to make it better and better. But I think I'll have a better chance of getting my methodology started with 3. Now, the hard part is this table is not perfectly level, and that's going to be a problem, but maybe I can get them equidistant apart. Use this toothpick, and I found this off camera. This works pretty well. If I can get them equidistant, now I have a much better chance of getting them to roll. And you can see right away, this thing rolls unbelievably well. I'll try and get a few close-ups here also. All right, I'm going to stop this and I'm going to hit reset and I'm going to time this one. I think what I'll do is I'll hit start and is just give it, I know this is not going to be a perfect method, but I'll just try to give the same amount of twist each time. And then once I figure out a better plan on how to twist this, I'll come back to that. All right, I'll hit start and give it a pretty good spin. Now, that spin, I could feel I vibrated it a little bit and it started swaying. So I'd like to do it again, but I'll just do all of my runs one time and then I can come back, and it turns out that that was a problem. So I'll put this back on. Clearly that was a problem. Can't use that piece of data. Just going to try it again. Maybe I'll put it closer to the camera so you can see this, although it makes it a little bit harder to spin it. All right, I'll hit my reset and I'll try it again. Start. I can see what's happening right away. I can see that two of the balls get close to one another like this, and then it's essentially just going to be like having two ball bearings. It becomes unstable. This is the essence of a long term. You just are going to run into problem after problem after problem. So I'm going to try this again. I think I need to give it a really nice smooth spin. And if I can't do that, I'm going to go back and start in the other direction, because as I have more bearings, I'm now making another claim. I bet you it's going to become more stable every bearing that I add. So I now have two claims. My one claim is I think it'll end up spinning longer with fewer bearings, but it's going to sway more. As I add more bearings or balls to my races, I have a feeling that it's going to become much more stable. All right, I'm going to try this again. So I'll hit reset, start. That was a pretty good rotation I could feel. It's not wobbling as much. What I'll do is I'll get a second camera on here so you can see the top and the bottom. But I think this run is going to be fine. Let's see what it does. And then I'll just put that value right here, and I'll do this for each one of them. It's going to take quite a bit of time to go through all of these. Maybe I could do those off camera. Once I get all the values, I can bring you back in. Spinning really nicely right now. Smooth. I'll get a close-up of this. We're at 40 seconds. When you look really close at this, it is actually a beautiful phenomenon. 49, 50. It might go for an entire minute. This is a lot easier to measure than when I had this fully packed where I couldn't even get it to go for a second. 10, a minute 12, minute 13, 14, 15, minute 20. So that's going to be 80 seconds. I'll just put that in right now. And then I'll repeat this process. I'll take a bearing here. And of course, this is going to end up, as we already saw, different runs are going to give different results. So one of the rules that I'll come up with as I'm doing my long term is, as long as it doesn't catastrophically fail, I'll use that run. But if it ends up falling apart, then I can't use it. So I'll put 4. I'll try my best to get them equidistant apart from one another. And now I'm recognizing there's a problem instantly that I can see. Because 3 points make a plane, one bearing, when it's not under load like this, is always going to be free to move. I don't know if you can see this one, but it's not actually touching. You have the 3 points, so I have a feeling this 4th bearing, maybe I could put a little pressure on it right there to keep it from moving, just to keep them equidistant, and I'll try this again. All right. Put that one over there. I think that's probably about as good as I'm going to get it. And then I'll reset. And I'll start. That was another pretty good run right there. I'll let this one go down. I think it's going to be closer No, actually, I think it's going to end up being less. And here's why. Look, these two spheres, oh, this one might fall apart. I don't know if you can see, but I've got 2 and 2. They're right next to one another. And once they start rubbing on one another, they're going to end up generating a lot of friction. I'll draw that out as soon as I'm done here. But this one is slowing down quick. Still going to use it because they're not touching and it's not wobbling. All right, 54. So drop dramatically. And I'll go on and on with these. So let me add one more. I'll get this started. And then I really want to show you a good camera angle on these because it really is a beautiful thing. All right, this is a little harder than I thought. But this is how long terms work out. You just get started. You end up making adjustments. You can always redo your data, which you'll probably do over and over. Let me get this one started. Reset. That felt like a nice rotation there also. You can see several of the balls are starting to get near one another, but it sounds pretty smooth. After this one, I'll probably do them off camera. Slowing down a little bit quicker. We're at 30 seconds. $47. Maybe I'll do the rest of these off camera. All right, I wanted to explain when two of these spheres touch one another. Look, think of each one of these as being one of the spheres. If one is trying to roll in this direction like this, and it touches another one of these, notice it wants to fight against this second one. And because of that, you're going to have this friction either between this contact point right here or on the ground. Let me draw this out. Now, I want to leave this part here because what do you do when you collect data? You make graphs with it. So we're going to leave that room there, but I'll try and draw this maybe off to the side here so we have plenty of room. Let's just think of this as being the tabletop right here. I'll just make a flat surface like this. And if I were to take, just use one of these, and let's put this one right in here, like so. Notice this is going to end up having some force normal. That is, the ground is pushing up on it. I want to show that they're actually touching here. So we'll have a little bit of touching there. But if I have a second one, and this one is trying to roll in that direction as it's moving with some velocity, well, a second one of these, and I'll try and make sure it's touching this time. When they're touching right here, because of the rotation of this first ball, it's going to end up trying to cause this other ball to rotate the other way. Now, of course, it doesn't want to rotate that other way. So you have a little bit of force between these two that are going to end up generating a little bit of friction, because I don't think that's going to be anywhere near this force normal here. Let me see if I can draw that a little darker there. Force normal. So what we'll end up having is when you have two of these going together, they're necessarily going to be trying to slow one another down. So the longer I can keep them apart, the better, but it's pretty hard to do. So sometimes you just get lucky. Should probably take multiple trials. But this is what we're after with our long-term projects. We don't want to just collect data. We also want to provide explanations. And every few minutes, every new thing that we do here, we end up getting another question, maybe making another claim, and so on. All right, now I'd like to get a couple close-ups of this. All right, it's very important to keep these balanced. If they're not balanced, they'll catastrophically fail. You can already see how it's wobbling. When I get this to spin and these two get closer and closer, it almost becomes like two balls trying to support this. It's unstable and it falls apart. Let me see if I can get this started. Like I said, catastrophic. All right, it's very important to keep these balanced. If they're not balanced, they'll catastrophically fail. You can already see how it's wobbling. When I get this to spin and these two get closer and closer, it almost becomes like two balls trying to support this. It's unstable and it falls apart. Let me see if I can get this started. Like I said, catastrophic. All right, so I already found out that if you only have two bearings, here, I'll just pull this off. Off camera, I just redid the 5-ball bearings again. I'm going to do most of these off camera. But I just wanted to make sure that I get 47 again. I got really close. I got like 45. So I feel like I can replicate this pretty well. But look, if we only have two bearings, we know that this will end up wobbling and it'll fall apart. We also now know that if my bearings get really close, they almost act like they're going to be one bearing and I lose stability. In that last shot we saw, it was catastrophic. Well, you know, this is also what makes a really good long term. It's generative. You come up with even new ideas and better ideas. Like now that I had a top view of what was happening with that bearing when I was in this condition, I could actually measure the wobble up here and be able to predict what the chances of this surviving are. I mean, look at that wobble. So again, a good long term is one that you keep finding new ideas. Now, before I get distracted too much, I do want to finish off just how does the number of balls affect the rotation time. And then, as I said before, we're going to make a series of these and we'll investigate each one of these. We'll put them all together. We'll present it as a big long term. And this is exactly how our students do it. All right, so I'm going to put on, I think I'm now at 6. And again, I will try my best, at least while I have fewer of these. What do I got? 3 and 3. Keep these apart. We're not going to show every single one of these. Maybe I can, and you could fast forward them, but I think that would be a little bit boring. Let's see if I can. I think the best methodology is just to put them in first and then try to move them apart. And maybe I'll just show a couple brief clips of these, but I'll get each one of these started. I'm going to fill this in, then we'll make a graph. One of the other things that I can start to say right away is, well, I know it's going to, the time is going to decrease as I add more and more of these balls to the ball bearing. The question is it a linear pattern or is it going to drop off quicker and quicker or less quick? So that'll be interesting. All right, let me go ahead and do these. 38. All right, I probably should have kept videoing these because these are going very quick now. And I'm going to be adding number 16 here. And sometimes you can feel when you get a better twist to begin with. Like that one, I knew as soon as I did it, I had a really good twist. And this one, maybe not as much. But whatever they are, we're going to keep them, unless they catastrophically fall off. All right, so now I'm at 16. All right, start. And I'm trying to be consistent each time, but this one's going to be pretty quick here. Looks like about 10 and a half. We'll just call it 10 on this one. Okay, and then I'll add another one of these. So now I'm at 17. So this is basically almost filled up completely. I can't really get any more space between them. So I'll just try it, reset, and then start. And I'm always off by a little bit when I hit this. We're down to 6 seconds there, so I'll put 6 right here. And then this is going to be filled up completely. Now, this is going to be where everyone literally has to touch the other one. So they are all crammed side to side. And in fact, this is maybe a little bit too full. But these do not want to rotate at all because I'll get a close-up of this. All right, to show you what I was talking about, I'm going to stand behind here because if I stand over there, camera tends to pick me up instead of these ball bearings. But you'll notice they don't want to roll. They're literally bound next to each other so tightly. So I think when you have a full set like this, you're going to have serious problems. So you can see this would be the most extreme case. They're not actually rolling. They have as much contact between them as they do the top and the bottom. And this really just does not want to move. You could see they are literally pushing on each other so hard, they don't want to rotate. So let me hit reset and then start. And then it's like a half second. I'm just going to put a half second. I don't know what else to do. So I'll put 0.5. All right. So now that we've got all this data, the very best way to see patterns in your data is to make a graph. So I'll put balls across here and then I'll put time up here. Let me get the axis drawn out. Put the graph on here so we could start to plot our points. I have number of spheres or balls there, and that's the thing that we ended up changing. So we put that along the x-axis. And we also call that the independent, and the dependent would respond to the changes that we made. Now, I put 0, 1, 2 here, even though we can't have a bearing that has 0, 1, or 2. But those are just stylistic decisions that you can make. But we'll call this preliminary data. We'll build on this in other videos, but let's see if we can answer this very quickly. At 3, I'm at 80, so I'll put a dot here. And then 4, I'm at 54, so about here-ish, 54-ish. And then 5, I'm at 47, so 47. 6, I'm at 38. 7, I'm at 36, about here. 8, I'm at 33. Somewhere down here-ish. 9, I'm at 22, so it jumps down a bit. 10, 16, so 10, about 16. 11, 15, about halfway here. 12, 13. 13 is 11, almost at the 10 mark. 14 is 14, so up a little bit. 15 is 9, so I'm now down below my 10. 16 is at 10, which is a little bit above. And then 17 is 6, so I'm about halfway. And then 18.5, so basically I'm down here. All right, so that's our general pattern that we're seeing. We can see this kind of swooping down. I don't have dots in between there, so we can either leave them as individual dots and say that's our pattern, or you could say, well, the general pattern, if you'd like, not saying that we have all this data, but in general we might say, well, it looks something like that kind of pattern. So either way, what have we found? Well, as I increase the number of ball bearings, the time that this rotates definitely decreases. That we can say for sure. So we'll leave it at that. That's the first part of this series on how to do a long term. We'll come back and we'll do some other things with this bearing. But this is how you get started on a long term. And this is your quiz for today. Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe. And if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.